So, good morning all. I welcome you all to my talk, Finding Nemo Faster, diving into fast image and depth recovery from an underwater image. So, myself Nisha Varghese, I am from Image Processing and Computer Vision Lab from Electrical Engineering Department, IIT Madras. So, as you all know, Finding Nemo is an animated movie which describes the journey of a clownfish who was trying to find out his son Nemo. So, my research topic is diving into fast image and depth recovery from an underwater image. So, it is an underwater navigation problem. So, as we go through underwater, we can take underwater videos, and from single image I can find the clean image as well as the depth very quickly in real time, so that we can find the Nemo faster. So, I want to emphasize three phrases from my topic: fast, image and depth from a single underwater image. So, how underwater images look like? So, if you place a camera inside underwater, so the captured images will be having a haziness in it, and there will be color distortions in the captured images. So, these are some examples, sample images from underwater data sets. As you can see, the captured images have haziness in it, and the original color is actually lost after capturing. So, we consider these types of images captured by a visible light camera, and it is captured under natural illumination and captured within the shallow depth of the sea. So, coming to underwater surveillance, as you all know in the left side, so underwater robots will be moving like this and it will capture images. So, in the right side you can see the captured images have, as I have explained in the last slide, captured videos will be having haziness in it and the color will be distorted. So, can we get a clear vision from the hazy underwater views? That is the first question. So, we have to go for underwater image restoration. So, say we have a color distorted and hazy underwater image. From that we have to find the restored image. Restored image will have all the colors restored back. So, the process is from the hazy underwater image we have to find out the restored image. So, this is one of the output from my method. Then comes depth from an image. So, what do you mean by depth from an image? So, consider this video. Here this underwater robot is passing very quickly through underwater. So, it will have a camera in it. So, it will capture different images, but it should not collide with the underwater objects. So, it has to determine the depth from the camera to the underwater objects, so that there will not be any collision. So, we have to determine depth from a single image. So, here an example of depth from a single image is given. As you can see, so as a human being I can say that this portion is actually near to my eye and this portion is actually far away from my eye. So, that amount of depth information. So, this portion has a lesser depth and this portion has a larger depth. So, this lesser depth I have to represent using a color code. So, that brighter portion gives the lesser depth value and the darker portion gives the larger depth value. So, there is a deviation of depth from this point to this point. So, that I have shown there. So, this is one of the output from my method. So, the goal is I have so underwater robots will be passing through the underwater. It will capture underwater images, and from single underwater I have to find out depth map as well as the restored image simultaneously in real time. So, as an example, if I have an underwater image like this, I have to get the restored image as well as the depth. Here you can see these portions are actually near to my eye, right. So, depth map should have brighter portions in that portions. So, those portions are actually far away, that portions will have darker color. So, how current works deal with this problem? So, currently there are traditional methods as well as deep learning based methods for finding depth and image from a single underwater image. So, we will first go to traditional methods. Traditional methods use underwater image formation model for optimization. So, An underwater image we can consider as a function of clean image as well as a depth. So, they have a single underwater image with them. From a single underwater image, they have to find out clean image and depth. So, this is a single underwater image they have. So, different combination of this clean image and depth will give the same underwater image, right. So, they have to use a prior knowledge. Prior knowledge is some knowledge we have, right. The restored image should be like this. So, that prior knowledge also we have to club together with this underwater image for the optimization. So, at first some random output it will find, then again they will be passed to the function to find the input underwater image, and using the error between the output and input they will again optimize. Next output will come, then again underwater image will be formed, again this optimization will be continued to get a good restored image as well as a depth. But that is so the advantage is that for traditional method there is no training is required, but the optimization process needs a number of iterations. So, it leads to delay. So that we can't use these traditional methods in our application because we need real time outputs. Then comes deep learning based methods. Say we have a deep learning network for depth estimation like this. So, it should be trained before. Here we have a deep learning network for image restoration. So, it should be trained with input underwater images and the ground truth depth map. So, the disadvantage of this underwater restoration and depth estimation is that, so for underwater it is difficult to get the depth ground truth as well as the restored ground truth. So, the first step for this deep learning based network is to generate training data sets. So, in the case of underwater, people typically use this terrestrial images, that is above water images, and they have its ground truth. They will find an underwater image corresponding to this image, and they will call this as underwater image and this as its depth. So, using this underwater image and depth, they will train this deep learning based network. But we can see that this underwater image is not real, it is actually synthetically generated underwater image. In the case of restoration also, people take this underwater image and they use different restoration methods, because in underwater we do not know what is exact color, right. So, we do not know the idea of the ground truth. So, people actually use different restoration methods and they will find different outputs. From different outputs they will take some best one and they will name it as ground truth, and this underwater image and this ground truth will be used for training this deep learning based network. So, deep learning network is fast, but it needs data set for training, but the data set or ground truth is not real. So, that is a problem with deep learning based network. So, how should we approach our problem? So, we should get fast output. So, we have to go to deep learning based networks, but we should avoid supervision with ground truth. So, what is new in our work? So, there is no need of paired data set in my work. So, we can call the network as self supervised. Self supervised means only the input underwater image will be used for training, no ground truth will be used for training. Then a single network will give both the depth map and restored image simultaneously, and will get real time outputs in 18 milliseconds for a 512 by 512 image, and it combines deep learning and mathematical model. So, how can I club this mathematical model into deep learning? So, I have used two mathematical models. First one is underwater image formation model. Here you can see, so underwater image I can be represented as j into e raised to minus beta d plus 1 minus e raised to minus beta d into a. The first term gives, so j is the clean image, e raised to minus beta d is the attenuation factor. So, how much it is attenuated after capturing? The e raised to minus beta d determines how the attenuation of j to get the underwater image I. The second term gives the backscatter effect inside the water. So, we have to we have the underwater image I with us. We have to find out j and depth d from the given underwater image. So, how can I form a deep learning network that gives j and this depth. So, I have input underwater image. I will split this underwater image into its components, A e raised to minus beta d and beta. So, for that I am using Gaussian blur to find A. I have followed the state of the art methods to find A. A is the global background light. Then I am using 3 networks, networks 1, 2, 3 to find J e raised to minus beta d and beta. Then I combine these disentangled components to get the I back. So, I can say that this I should be equal to I. So, I can give a constraint that the output I after combining this disentangled component should be equal to the input I. So, this is one of the constraints I am using in this deep learning network to return the correct J e raised to minus beta d and beta. But this is a loose constraint because any combination of this A j e raised to minus beta d can give the I back. So, I have to use another constraint also, that is a geometry between 2 adjacent images. Say we have 2 images J1 and J2, and if you have the depth map of first image, if you have the depth of first image and if you have the relative camera pose between 2 images. Say J1 is captured with this angle and J2 is captured with the another pose of the camera. If you know the relative camera pose between J1 and J2 and the depth of the first image, then the second image can be warped to the view of the first image. Second image can be warped to the first view of the first image. Then I can say that the warped image and J1 should be equal. So, if there is a correct depth only, I can warp J2 in the view of the J1. So, this is the second constraint I am using. So, here I am using underwater image formation model, here I am using geometry between 2 adjacent images. So, for my training I am using 2 adjacent images from an underwater video. So, when you consider this, consider this underwater image. Here as you can see, the farther points, that if the depth is more, haziness is more, right. So, if the depth is more, the attenuation factor will be high. So, attenuation of J will be more. So, that factor only I am using by using this equation. Then for the next one, so actually we perceive depth from the images captured by our 2 eyes, right. So, in the left eye we will capture some image like this. So, in the right eye, so there will be a shift of images captured between the left eye and right eye views. So, using the disparity between 2 images only, we actually perceive the depth of that object. So, this idea only I am using here, I am using the geometry between 2 adjacent images. So, here I am using depth from haze, here I am using depth from 2 images. So, how can you club these 2 mathematical models during training? So, I have 2 images from my underwater video. These are 2 adjacent images from the underwater video, I1 and I2. First I1 is disentangled into its components, then it will be combined to get I1 back, that I have explained. So, here J is my clean image that I can obtain from here, then I2 is also cleaned using network 1 to get J2. So, I have clean images from 2 images I1 and I2, then depth I find by analytically using e raised to minus beta d and beta. I can use logarithm to find depth from these 2 outputs. So, I have J1, J2 and depth. So, J1 and J2 and depth will be used to warp the second image to the view of the first image. So, this is my training process. So, if the depth is correct only, I will get this J1 is equal to J1. So, if the depth is wrong, I will get another J1 here. So, I can use 2 constraints here, loss between I dash and I1 and loss between J1 dash and J1. So, these are 2 constraints I am using. If the depth is correct, then this constraints will be obeyed. If the depth is correct here, then only this J and e raised to minus beta d will be correct, as I am using a mathematical model. So, once the training is done, all these networks will be trained already. So, I need to use, for testing case, I need to use only 1 image. So, 1 image will go to SRNet is network 1. to get the clean image here, and TMNet and BetaNet are network 2 and network 3. From there I will get the depth here. So, during testing time I just need to pass this a clean hazy underwater image to network 1, network 2, network 3 to get this J and D. So, so this can be done very fast. So, that is why I am getting both the outputs in real time. So, this is one example of our output. So, here I have underwater image. So, this is the restored image and this is the depth map. Actually, I am passing only one image to get one output. Here I am just showing a video output. So, as you can see, these portions have lesser depth. So, there is a variation of depth from this point to this point, that you can see from this depth map, and both the outputs obtained in 18 milliseconds only for one image. Coming to the generalization ability, while considering deep learning network like this, so they will be trained with using some ground truth and some data sets, right. So, if you are showing some other images from other data set, they may not work well. But in our case, so it is actually self-supervised network. We did not use any ground truth for training. So, generalization ability of our network is very high. Here one example I have shown. Here you can see some other data set from some image from other data set. This is depth from some state of the art method. This is our depth. You can see the structure of this rock is actually lost here using the state of the art method, but our depth is better. Here also the restoration output, you can see our restoration outputs is better. So, these are some depth map and restored image outputs of some random images, and note that both the outputs are obtained simultaneously in real time in 18 milliseconds. So, our network is fully self-supervised, it does not use any ground truth for training, and the restored image and depth from a single underwater image we can get, and real time outputs it will give, and it is generalizable to any input underwater image. Thank you.